Welcome back to this tutorial. Now we are going to solve more example on capacitor. So in our last video we solved like 5 examples in which we saw different way they can set question under capacitor. So now we are still going to solve like 5 more examples. So but before you look at this solution, try and pause the video and quickly copy the question, solve the question ahead, and cross-check the answer with the answer we are going to get. Also, if you have any question, maybe you have any question disturbing you, so subscribe to this channel and test the question to the inbox and send it. Then we try to look at the question. Now, let's solve this question. Question number 1. They said, find the capacitance of a capacitor consisting of a sphere and a concentric spherical conductor of radius 8 cm and 12 cm respectively. That's the first question. That is, our rate is what? The rate is equal to, let's say R1 is equal to 8 cm and R2 is equal to 12 centimeter. So, and also we are asked in question B to find the potential difference if the current supply is equal to 5 ampere, if the current supply to this source is 5 ampere, and at a time interval of 3.5 seconds. Now, what are we going to do? Here we have to think of the derivation we've done earlier. So we said that if we have a capacitor for a what? For a concentric sphere. So we have the formula to be what? Our formula is C to be equal to 4 pi E naught B minus A over AB. So we are going to apply the formula now. We said that C to be equal to 4 pi E naught R2 R1. So R2 minus R1 over R2 R1. So we prove this formula. So now we are going to apply the formula now. From here we have something like this when we calculate it. 1 over R1 minus 1 over R2. So by the time we take the LCM, we have R2 minus R1, R2 minus R1 over R1, R2. So this is the what? This is the potential difference then. So if we substitute this, you know, then by taking this one up, this one will be up like this and this one will go down. So because we actually calculate the potential difference when we take the integration, so now we now relate it with respect to what? With respect to our capacitance. Now if we look at this one is just a direct question. 8.85 times 10 raised to the power minus 12 multiplied by R2 is. So if you look at this one, we see that this one is in centimeter and this one is also in centimeter. So we don't need to convert it because the centimeter we have to cancel the centimeter. So that is, this one will just be 8 multiplied by 12 divided by 12 minus 8. If you multiply this one by this one, so it will be centimeter. Okay, let's just convert it. Centimeter square over centimeter. So we are still going to have 1 centimeter, which will give us problem. Let's just convert everything. Then this one will be 12 times 10 raised to the power minus 2 multiplied by 8 times 10 raised to the power minus 2 divided by R2 is the same thing as 0.12 minus 0.08. That is 8 times 10 raised to the power minus 2. Then our capacitance will be equal to 4 pi If we press this correctly, the capacitance will be 2.669 times 10 raised to power minus 11 farad. The unit is in farad, but we know that 10 raised to power minus 9 is nano. So if you try to remove 10 raised to power minus 9 here, that is, if you say 10 raised to power 9, so we are going to have what? Times 10 raised to power minus 9. Sorry. 10 raised to power minus 11 is the same thing as 10 raised to power 9 times 10 raised to power minus 2. So, and 10 raised to power minus 2, or we can leave it in picofarad, and pico is 10 raised to power minus 12. So, if I'm to say this one multiplied by 10 raised to power minus 1 times 10 raised to power 1. So we are going to have what? So if I multiply this by this, I'm going to have minus 12. If I multiply 10 by this, I'm going to have 26. Then this is 26.69 picofarad. So this is how to convert, because the option may be in terms of pico. If the option is in terms of nano, then we just say 10 raised to power minus 11 is equal to what? It's the same thing as 10 raised to power minus 9 times 10 raised to power minus 2. This is what? Nano. So we can just say 2, then 10 raised to power minus 2. If I multiply it with this one, so I'm going to have 2.669 times 10 raised to power minus 2 nanofarad. So we can leave it also in this. So we can also convert it into this. It depends on the way we want to leave our answer. So B, question B, we are asked to find the potential difference across these capacitance if the current supplied to the source is this. So to find this, we know that this is Q to be equal to CV, and the potential difference is equal to Q all over C, but our Q is equal to what? IT, which is the same thing as 5 times 3.5. Then our charge is equal to 17.5 coulomb. Now, by substituting this, we are going to have 17.5 divided by 26.69 picofarad. So let's just remove the pico. So let's say times 10 raised to power our actual answer. We can use our actual answer, which is 26. This one is the same thing as 76 times 2 is 9 times 10 raised to power minus 12, which is now equal to minus 12. Then we are going to have 6.556 times 10 raised to power 11 volts. Then we have high voltage. We have high voltage across this. Okay. So this is the solution, a simple solution to this problem. Now we are going to look at the question number 2. Question number 2. A capacitor is rated 4 picofarad plus or minus 15%. Which of the following capacitance is outside the capacitance range? So we have to clean this. So, question number 2 says, a capacitor is rated 44 picofarad plus or minus 15%. which of the following capacitance is outside the capacitance range? We want to know which of these is in the range when it is, that is, the range of this capacitance range will be equal to 44 picofarad plus 15% minus 15%, which is the minimum value we can get, and 44 picofarad plus 15%, which is the maximum value we can have. Now let's find the range. 15% of this capacitance, that is 15% of 44 picofarad, which is the same thing as 15 divided by 100 multiplied by 44. So we can have 6.6 picofarad. So the 15% of this capacitance is 6.6. Our range will now be equal to what? 44 minus 66 minus 6.6 picofarad, comma 44 plus 6.6 picofarad, which is the same thing as we have our range to be 37.4 picofarad, comma 50.6 picofarad. So now it means that any value between 37.4 and 50.6 is in the range. Option A, if you look at option A, well, they say that A is 38.4 picofarad. If you look at this, we see that 38 is inside this range because 38 is greater than 37. So clearly, option A is in the range. If you look at option B, 50.3 microfarad. If 50.3 is not up to this, therefore option B is also in the range. If you look at this, option C is 61.2 microfarad, which is greater than the maximum value we can get. Likewise, option D is also not in range, and E is also in range. Therefore, we can say A, B, and E are in the what? Are in the range. Why? Option C and D are outside the range. So this is just a typical example. So different way of question can be given to us. We have the thing we need to do is think and see how we can tackle the question. Now let's look at question number 3. Question number 3 says that 12 0.08 microfarad capacitor are connected in series. Then the total capacitance and the charge on the combination when it is connected to a source of 200 volts is 12 0.8. It means that we have a series combination of 12 things. Like this, 1, 2, 3, 4, up to 12. And each of them is 0.08 microfarad, 0.08 microfarad. Each of them like this have this, and we have 12. Now to calculate the effective capacitance on this, we have to say 1 over CT is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. This is the general formula to find the capacitance when we have if we have many capacitance that are in series with each other, then 1 over C1, 1 over C2 plus up to what? 1 over Cn. Let's assume we do not know the amount of the capacitance. Let's say we have unlimited number of capacitance combining in series. So we are going to have this. Now, to know our effective capacitance, it means that in case we have something like this, instead of us to be saying 1 over this plus 1 over this plus 1 over this, we just say that our CT, effective capacitance, is equal to the C over the number of the capacitance present inside. Now, we are going to use this formula. So this formula is to find for series. Let's say we also have different arrangements. Let's say we also have different arrangement of capacitor in parallel. Let's say we have something like this. So let's say we have different arrangement of parallel combination. You know that to calculate for parallel, our CT is equal to C1 plus C2 plus C3 plus Cn. So to calculate the effective capacitance for parallel, we just say CT to be equal to NC. The number of the amount of parallel combination we have multiplied by the each capacitance. So we normally use this to calculate for parallel. So these are the derivation. Now let's use this to solve this question. Now in the question we say we have 0.08 microfarad. That is, the capacitance is 0.08 microfarad capacitor, which are connected in series. They now say the total capacitance and the charge on the combination. So when it is connected, they say we should find the total capacitance and the charge on the combination when it is connected to a source of what? 200 volts. Now, with this formula, we said that CT is equal to C over N. And the number of the capacitance connected is equal to what? Is 12. So, we are going to say 0.08 times 10 raised to the power minus 6 divided by 12. Then we can find the capacitance connected. Our effective capacitance is 6.666 times 10 raised to the power minus 9 farad, which is approximate to be 6.7 nanofarad. So it will be 6.7 nanofarad. Now to calculate the charge on this, on the combination, so the charge on the combination will now be Q to be equal to CTV. So which is the same thing as 6.667 times 10 exponential minus 9 multiplied by 200. Then the charge is the same thing as 1.333 times 10 raised to the power minus 6 coulomb. So the charge on it can be approximate to be 1.3 microcoulomb, since micro is 10 raised to the power minus 6. So this is the simple solution for this simple problem. So with this, we see that we solve different questions on capacitor. So they can actually set question in different way. So then another thing that can happen in capacitor is that there is what we call equipartition of energy. So, and this equipartition of energy, is just when, you know, from our knowledge, we say that energy can neither be created nor destroyed, but can be transformed from one form to another. We can have a case in which a chemical energy is being transferred into a what? Mechanical energy. In a way in which electrical energy is being transferred into mechanical energy. So the same thing can happen, and it is very realistic. You know, I explained earlier in our previous class, we said that let's say we have a force. In physics, we normally deal with a body to be balanced. So that is what we call equilibrium of forces. We say, let's say that a force is acting on a body like this, another force is acting on the body with this in this direction, another force is acting in this direction, another force is acting in this direction. Let's say these different forces are from different force. Let's say we have magnetic force, this is electric force, this is gravitational force. Let's say this is electric force, different force and gravitational force. So now, the body we want to move with respect to the one that have bigger energy. Let's say that the energy of the magnetic is greater than the gravitational force. Then it will be approaching to the magnetic force. But since another force is acting on it, different three forces also applying to the body. Then at some time it will be dragging towards each forces attracting it. So for this body to be in resolve, to be balanced, then we have to apply the same force of electric force to be the same thing as the force of gravitational force, the magnetic force. Then when all these forces equal to each other, we say that this is what we call equipartition of forces. Then the same thing for the energy. So we are going to have equipartition of energy, in which we can say that the work done in capacitor, which is what? Half CV squared, is equal to half QV, half Q square over C. It can be equal to the work done in electric, the energy of electricity, which is IVT, which is equal to I square RT, which is equal to, it can also be equal to, in terms of quantum, we can have MC square, half mc square, which is, it can equal to 8f. So like that. So this is what we call, and it can equal to what? MC change in temperature. So this is what we call equipartition of energy. So we can solve any question with respect to this and so on. Now we are going to look at another example in the case when we have, let's say we have combination of parallel and series together. So this will be example 4. We say two capacitor microfarad and 5 microfarad respectively are joined capacitor of 4 microfarad Now, this is the second example. The fourth example. Two capacitors, 4 microfarad and 5 microfarad respectively are joined in parallel, and the third capacitor of 4 microfarad is joined in series with them. What capacitors should be joined in parallel with the third capacitor so that the total capacitance of the circuit is 5 microfarad? Now, to solve this, we have to first understand the question and sketch a diagram for the interpretation of the question. Now, the first thing said that two capacitors are connected in parallel, and we know this is how a circuit can be connected in parallel form. That is, let's say this is capacitor A. This is CA, which is connected in with 4 microfarad and 5 microfarad. They now say, and the third capacitor of 4 microfarad is joined. So, since if we resolve this one into parallel, we are going to have something like this, which will be in series with another capacitance. Then it will be in series with this. The third one, which is of 4 microfarad. So they now say that what capacitance should be joined in parallel with the third. That is, what capacitance should be joined with this third one in parallel also. So let's say we join this one in parallel with this. So, but what capacitor? It means we are looking for this capacitance, the fourth capacitance. So let's say this one is C1, this is C2, C3, and this is C4. Then the capacitance here, let's call it CB. Now, they now say the effective capacitance for all these things, the CT is equal to 5 microfarad. Now, what are we going to do? So this is the sketching for the statements. Now we can find, since we know that this thing will be in this form, when we find the parallel combination of this and find the parallel combination of this, then we are going to have something like this. We are going to have CA, CB, which is now connected in series. The CA and CB will now be connected in series. Now for CA, CA is equal to C1 plus C2. For CB, let's say this is equation 1. For CB, CB is equal to C3 plus C4, which is 2. Now from this one we can find our CA. Our CA can be equal to 4 plus 5, which is 9 microfarad. So this is the value for the combination of CA. For CB, CB is, we have the value for C3, which is 4 plus C4, everything in what? Microfarad. So this is the formula, this is the value for our CB. Now, we can try to look at the combination between this one and this. CT will be equal to CA, CB divided by CB plus CA. If we, since this one, CA and CB are in series, so you know we are going to have 1 over CT to be equal to 1 over CA plus 1 over CB. So 1 over CT can be equal to CB plus CA over CA CB. So if we take this one up, this one also will go up over CB plus CA. So that's how we get this. Now, And our CA, we already know our CA to be what? To be 9. If I inserted this value here, our CA is 9. 9 CB, let's say 9 CB divided by, okay, our CT, our effective capacitance is 5. 5 to be equal to 9 CB divided by CB plus our CA is also 9. So if I cross multiply here, so I'm going to have 5 CB plus 5 times 9, which is 45, is equal to 9 CB. So if I take this one to this side, I'm going to have 9 CB minus 5 CB to be equal to 45. I take this one to this side. So 4 CB is equal to 45 and CB is equal to 45 divided by 4, which is the same thing as 11.25 microfarad. Now, 11.25 microfarad. Since we know our CB, then definitely we can know the value of our C4. From, let's say this one is equation 3. From equation 3, CB is equal to 4 plus C4. So, and our value for CB is now equal to this. It means that C4 will be equal to 11.25 minus 4, which is the same thing as 7.25 microfarad. It means the value for C4 will be 7.25 microfarad. So this is the solution for this question. Let's look at more examples. Now, example 5, said how many three microfarad capacitor would be needed in series to store a charge of 2 coulomb with a potential difference of 200 volts across the capacitance. Now let's look at this question. The question says that how many 3 microfarad capacitor would be needed in series to store a charge of 2 coulomb with a potential difference of 200 volts across the capacitor. We can actually find 2 things here. Let's say the question, we are to change the question to parallel. So we can also find the number of the capacitance there. Now, earlier I said that if we have many numbers connected in series, we are going to have C all over N. So, and we said that how many 3 microfarad capacitor would be needed in series to store a charge of 2 coulomb with a potential difference of this. And our charge here is equal to 2 coulomb. Our potential difference is equal to 200 volts. Now, what are we going to do? So, our capacitance here is what? Is 3. So, we are going to have now, our effective capacitance from here, we know that Q is equal to CTV. So, clearly, our CT can be equal to Q all over V. So, we can use this to calculate the effective capacitance. So, which means this one can be the same thing as Q all over V to be equal to our capacitance here is what? That is 3, which is C all over N. And we want to find the value for the N. N will now be equal to CV all over Q, which is the same thing as the capacitance is 3 times 10 raised to the power minus 6 multiplied by volt, which is 200 volts, divided by the charge. The charge here is 2 coulomb. That is 2 times 10, sorry, 2. It's just 2. Now, if I press this correctly, we are going to have 3 times 10. So, our N is equal to 3 times 10 raised to the power minus 4. So the number of the capacitor needed to charge this to this is now equal to what? 3 times 10 raised to the power minus 4. Suppose our charge is greater than this. Let's say 2 times 10 raised to the power 2 times 10 raised to the power 3 coulomb. Here we are going to have 2 times 10 raised to the power 3. So which at the end of our answer we are going to have 2 times 10 raised to the power minus 1, which is 0.3. So this is the solution for this question. Now let's look at other example. The last example on this capacitor will be the plate of parallel plate capacitor are 0.5 centimeter apart. If potential difference of 2 times 10 raised to power 4 volts is applied across them. Calculate the capacitance and the charge on each plate. So this will be our last example on capacitor. Please endeavor to pause this video and try this question. So now the third solution: a parallel plate capacitor of distance 0.5 centimeter apart. If a potential difference of 2 times 10 raised to power 4 volts is applied across them, then we are asked to calculate the capacitance. We want to calculate the capacitance and the charge on each plate. The charge on each plate. Now, we know that the formula for finding the capacitance of a parallel plate capacitor is the same thing as E naught A over D. So by substituting this, so E naught A over D, so there is something mixing in the question. So we're supposed to have area. Let's say we have this constant 2 centimeter by 3 centimeter. So that is length and breadth. So we know that our area is equal to length times breadth, which is the same thing as 2 centimeter times 3 centimeter, which is 6 centimeter square. So if we are to calculate 6 centimeter square into meter, our area will be equal to 6 times 10 raised to power minus 4 meter. So the capacitance will now be 8.85 times 6 times 10 raised to power minus 4 divided by the distance between them is 0.5 times 10 raised to power minus 2. If we put this correctly, we are going to have this is 1.062 times 10 raised to power minus 12 coulomb. Sorry, microfarad. So if we this one is the same thing as say 1.062 picofarad. Now we are asked to calculate the charge on this capacitor. And we know that the formula to find this is Q is equal to CV. Then our Q will now be equal to 1.062 times 10 raised to power minus 12 multiplied by 2 times 10 raised to power 4, which is 2.124 times 10 raised to power minus 8 coulomb. So also another question that can be asked on this, we can be asked to find the work done on the plate of the capacitor, and also find the work done in discharging the capacitor, which is different thing. So, and I said earlier that if we are to find the work done on a capacitor, it's just half CV squared, which is half QV, which is also equal to half Q squared over C. We can just take any one and use it. And this is for the capacitor, the work done on the capacitor. So to find the work done in discharging or charging the capacitor, it is just be CV squared, which is QV, which is also equal to Q squared over C. So this is the difference between the two. So we are going to stop here for today. So please like and subscribe to this channel. Try and solve different questions under this capacitor, and if there is any question, as we have said earlier, so you should just try and send the question to the inbox. So thank you.